So yeah, just making sure everybody's got that Le Chatelier. This is like fun with Cobalt lab. That lab that's being stapled to the back of your packet for now. All right, champs, let's do this. So on the board, you see a question related to equilibrium, right? Well, the equilibrium constant is something we showed how to set up yesterday. We did a good job of looking at how does K, the equilibrium constant, relate to a graph? How does that relate to the extent of a reaction? When I say extent of a reaction, what do I mean by that? Shout it out. I need some good participation today. Say again? Well, it tells you, the extent of the reaction tells you about the K value, but what do I mean by extent of a reaction? Right, so how the extent of completion. So 100% completion means that the K value is what?
1.
So, but you'd be dividing by, if you have 100% completion, you have like all products, 0 reactants. Can you divide by 0?
It would be
Error, right? Infinity. It would be a very, 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 very large K value. So we essentially say it's approaching infinity because it's so huge. Completion reactions don't really have a K value associated with them because we can't really divide by 0. But if a reaction's like, I don't know, 2% completion, very much 2% products, 98% reactants, very much favors which side? The reactant side, right? So that question at the beginning where we did a warm-up, I think y'all's group did, Jacob, it was like, why would the reverse direction be favored over the forward direction? It's more related to the Gibbs free energy, the energy release, the stability of the products versus the reactants. So it does have to do a little bit with thermodynamic stability, which we'll learn how to calculate K from delta G soon. So now we're going to start plugging things in and write and calculate. So I'm going to recap a couple things from yesterday as we go, but we're doing a bunch of calculations, so have your calculator out and ready. You guys have a couple of the pieces of these problems in your packet. I'm going to have to like direct you because I didn't put the question number or the page numbers on here like I usually do. But this is under the upper left-hand side. It says rest of equilibrium constant PS. Do you see that? That's the question, just FYI. Okay, so equilibrium constant. Whenever you're writing your equilibrium constant, I actually want you to show your expression. I'm making this a requirement. So required, do exactly as I'm doing this because I don't want you to mess up with your exponents because that's where you just quickly overlook something. It's hard to kind of catch your mistakes when you don't see your mistakes, right? So what is the equilibrium constant expression for this example? Shout it out quickly. Concentration of C cubed over. Thank you. I appreciate the expedited responses so we can move through these examples. You have some time for practice today. Okay, so this says the equilibrium constant for the equation is shown to be 1.5 times 10 to the negative 8. Off the bat, you should know which side is favored. Say again? The reactants are highly favored, right? Very, very, very small K value. It's going to be highly favoring the reactants. So at the end, what you should find, and you might even realize this right now, the concentrations of A and B, which are reactants here, are 0.15 and 0.28. And then it says what's the concentration of C. Can you give me a relative value for C? Is C going to be higher or lower than A and B? Why lower?
Because it's less than 1 day, it's less than 1.
So this is it's not a valued, it's not favorable in the forward direction. So C is likely not forming in a high amount, so it should be low. So keep that in mind. C should be a low value. Okay, and that's going to kind of doubly confirm us when we actually calculate. So my C value is X. My values for A are 0.15 molar squared and 0.28 molar to the first. That's equal to my K value given to me of 1.5 times 10 to the negative 8. Tell me how you would solve this. Do not say solve in your calculator. I want to hear some math first.
Okay, so multiply everything on the bottom.
Multiply everything on the bottom and
then multiply that by.
Multiply by this.
And then
Okay.
cube root.
Then we'll cube root. Okay. So when you multiply these together and then times it by your 1.5 times 10 to the negative 8, you're going to get x cubed is equal to what? Go, somebody tell me that. Sorry, from my calculations over here. 10 to the negative 11. And that's molarity cubed, just FYI, because there are 3 molarity times molarity times molarity, right? Then you cube root it. So X, which is concentration of C, is equal to 4.556, is around 455 times 10 to the fourth, negative 4th molar. All right. Does that match our hypothesis? Yes, it's a very low value. It makes sense. The products are not favored. You should have very few products being formed. Relatively much more reactants that are present. Now these are conditions that say at equilibrium. Okay, hold on. I'm going to adjust this question because I wanted you to do an equilibrium first before I started doing more complex ones. So this question, if the equilibrium concentrations are blank, blank, and blank, what we were able to do is if it says at equilibrium, we're able to plug directly into the equilibrium constant. If it says at initial conditions, we're going to have to do something called an ice box or a rice box, which is what you guys read a little bit about. Ice box or a rice box is very similar to a BDA chart, but we're talking about equilibrium, so we don't use, like, in BDA, what units do you normally use? Moles, right? And at this point, we're not talking about moles in equilibrium. We're talking about what? Either concentration or, for gases, partial pressure. So we would use different quantities, which would give us a slightly different relative relationships so that we could actually compare something. So I'm doing this as an equilibrium example first. At equilibrium, plug your values in, solve for the other substance at equilibrium. Okay, so what about number 2? Graph this one. Not bad. Graph. What would you guys have expressed as a possibility for your graph here? Give me some characteristics about your graph. Okay, so you want to start with reactants high? Okay, so let's say looking at the relative quantities, you say there's or the rate of consumption of A as compared to the rate of consumption of B is 2 to 1 because of the mole ratio, right? Okay, so when you draw A going down versus B going down, how are the graphs going to look different? How much faster? Twice as fast. So your graph, when we graph these, it doesn't have to be absolutely perfect, but there should be a comparison that's very obvious. And so that graph slope should be similar to the ratios that they're consumed or producing. So A is going to kind of go down. That's I'm gonna scale back my steepness so I can have my other one being steep. So there's A going down. B, I'm going to make it maybe start a little higher because doesn't start with a higher concentration anyway? Yeah, 0.28. So I'm going to have it go down, but go down as steep or less steep? Less steep. Yeah, it's kind of like half as steep, right? Let's just call that B and this A. Okay, and then C, I'm going to start from here. How quickly, relatively, does it go up? Well, look at the ratio. The slope should be 3 times as fast, truly. So I'm going to start really low, and I'm going to go up fast, 3 times as fast, and then level out, right? So it's not beautiful, but I should see that this is faster as in terms of formation. This is 3 times as the slope, this is 2 times the slope, and this is 1 times the slope, basically, because of the stoichiometric relationships. And I have a better graph for you. Let me show you that from yesterday. I skipped over it yesterday to get to the guts of this. I have 2 more things to show you. So this is a good example of that, and that graph up there should give you some indication to the reaction, and that reaction I have highlighted. The stoichiometric relationships, 3 to 1 to 2, should match how these are represented on the graph. So you should see that hydrogen gas is being consumed 3 times faster than who? Nitrogen. So you can see that slope's much more steady. And then it's hard to see this difference, but you should see that ammonia is being formed twice as fast as nitrogen is consumed. So that's the beginning stuff up here. All of this, guys, this is kinetics. Doesn't this look just like kinetics when we were looking at the relative rates of consumption and production? And now we're looking at, okay, this is reacted. Now we're looking at what are their relative concentrations at equilibrium, and what does that tell me about the extent of the reaction in the forward direction or the reverse direction? So it's the same idea, it's just we're further along in the page now, okay? And then one more thing I told you yesterday. I have like highlights where I was going to show you something. So as it relates to kinetics, the information we spoke of yesterday was that equilibrium was the place in a reaction where the rate of the forward reaction equals the rate of the reverse reaction. The rates are equal. So I've set up a kind of a proof for you to show you the relationship here, just in case you see something like this later. So the rate of formation of the forward direction, which is forming B, is based on A being a reactant, true? Okay, and then the rate of the reverse direction, which is formation of A, from B is based on the concentration of B. And you'll see this as rate F and rate R, meaning rate forward and rate reverse. Well, if the rates are equal, I can set this equal to this, which I have done right here. And then if I am looking at equilibrium, I'm looking at the comparison or the ratio of the products to the reactants. So I've taken B and I divided by A, so A came over here, and I divided by KR, which is the rate law constant K, and I put it over here. So I got this. Well, then you're like, well, what does this even mean? This is the ratio of the products to reactants as it's compared to their rate laws. But truly, the ratio of the rate constants give us the K value for equilibrium. So the ratio of the forward direction versus the ratio of the reverse reaction rate gives us the extent of the reaction. So basically, if the forward direction is fast, has a high K value, correct? If the reverse direction is slow, what is its K value? Higher or lower? Lower. So if the forward direction is fast, meaning a high value, and the reverse direction is slow, meaning a low value, what does this give me for K? Something that's what? Greater than 1. And in something greater than 1, you tell me products are favored, right? Well, that would mean the products are favored. And that's probably true, because if the forward direction is happening faster than the reverse direction, or their relative comparisons of their rate law constants say that, then the products are favored. So there definitely is a relation to K, meaning rate law constant K, but truly it just informs us on the rate of, or the extent of the forward direction. So I just want to connect those dots for you before we move on to calculations now. Am I good to move on? If you get sleepy on me, I've caffeinated myself. You need to probably try that once a week. Go stand up at the lab station, because I'm going to be up here for a little while today. So the next part, I'm doing question 2 now, okay? Question 2. Carbon dioxide reacts with solid carbon to give carbon monoxide. What's that reaction? Reaction. I'm going to say equilibrates, okay? Equilibrates to... Oh, good. Okay, so we're balancing right now in our head. All right, and then what other piece of information is a solid point to note? Okay, so this is a solid, which is important because why? Right, we would exclude it from our equilibrium constant. Expression is how we want to say that, because this is an equation. Expression is how we set up our relative comparisons. So K for the equilibrium expression, I'm only going to let K EQ just to be cheap and go with equilibrium constant. How would I set this up? Concentration of carbon monoxide to the second power over carbon dioxide to the first power. Okay, ignoring the constant or the C value because it's a solid. Okay, do I have concentrations given to me in this problem? No, I don't have concentrations. I have moles and liters. Okay, so what would I be putting in here to calculate my own concentration? 0.27 moles over 5 liters to get molarity. Square that over 0.58. Let me squat so that I'm not in somebody's way. Over 5 liters, because that's our molarity, right, to the first power. Go ahead and calculate. And see where at. There it is. It doesn't hurt my feelings if you stand up, but it does hurt my feelings if you close your eyes and fall asleep. Thank you. All right, what's that value? Point. Say it loud and proud. I got 0.025. Thank you, Levi. Okay, so 0.025. Did you not square it? Yeah. Shame. That's why I said, if you write it and then you write it again, you better put it in your calculator, right? So if you don't write the squared one time, your body does, or your mind doesn't think to put it in there. So if you write it numerous times, it's forcing you to think about it. It's forcing you to identify it for your calculations. What does this value mean about my reaction? So it favors the formation of the reactants, which means it favors the reverse direction, the reverse reaction. Okie dokie. So these are all established at different or at a specific temperature. I'll note a couple ideas about temperature's relationships later with this, but from here I'd like to do some more calculations with this. So yesterday we spoke of how Kp and Kc are related. I call it the politically correct formula, so you remember the order that the K's are in the equation. Why do I say politically correct? It's because it goes, what's first? Pressure and then concentration. So that's this right here. This is on your sheet as well, if I'm lying to you. No, I'm not. Okay, so it's the second quadrant on your sheet. So consider this equilibrium reaction shown. Sulfur dioxide plus oxygen yields 2 sulfur trioxides. Write the expression for Kp. Kp is equal to? No, expression for Kp for this reaction. What I'm saying is I want the equilibrium constant expression for this reaction. So I'm not using concentrations. I'm using partial pressures. It's the same thing we've been doing, it's just with partial pressures instead. Partial pressure of sulfur trioxide squared over sulfur dioxide squared times, beautiful, that's a fraction, right? So that's what I mean by expression. Later we're actually going to use the Kp expression, or the equation. Okay, so the Kp for the reaction shown in the first one is 0.25. So Kp is equal to 0.25. Determine the value of Kp for the reaction shown below. Jack says it's what? It's flipped. So if the reaction is flipped in equilibrium, what do we do to the K value? Right, so we invert the K value. We don't do negative, we don't raise it to the, well actually we can raise it to -1, it's the same thing. So we're going to do Kp either to the -1, which is the same thing as me saying K, or 1 over Kp. You do this in your head. What's 1 over 0.25? 4. How many quarters go in a dollar? 4. Okay, that's how you can think about your fractions. So now, what you can tell me is, which is the favored reaction? The forward reaction, or the way that this one's written, which is the reverse reaction? Which is favored? Reverse. You say that with question. Okay, you say that with no hesitation now. So Jacob says reverse, but why reverse?
Because it favors the carbons. It's greater than 1.
Okay, so the value of K in the reverse direction is greater than 1, which means that reaction is favored in the way it's written, which is written as the reverse direction. Are you picking up what I'm putting down? This reaction is favored in that direction.
Oh, I see.
This reaction is not favored in the way it's written right here. And it's likely because these guys are more stable, O2 and SO2, versus sulfur trioxide. Mostly about stability and like energy relationships. Okay, so the last piece of this is now taking information from Kp and finding Kc from that. So at a particular temperature, blah, 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 all species are gaseous. Determine the Kc for the formation of hydrochloric acid at this temperature. So I'm looking for Kc. Do I have information for Kc? Hold on, let's pause. Do I have information for Kc or Kt for this particular one? Kc, so I'm given moles and meters, right? And then you'll see later it says determine the Kp for this reaction, which will take information, which is our Kc at that point, and plug it into what equation? The politically correct and sulfur Kp. So we're quickly doing this one, okay? What's my reaction, by the way? It says formation of HCl, right? So what are we forming HCl from? How do I write hydrogen? H2 plus Cl, diatomic, thank you, and alright, so here HCl, and you're saying 2 of them to go ahead and balance that. So we're forming HCl from its elements. Everything's gaseous. How do I find, or let's do my expression first. What's my Kc expression? concentration of HCl squared over H2 times Cl2. Okay, what's my concentration of HCl? Or do I need to calculate that for us first? We can just do it within the expression, right? So 0.45 moles divided by, so, liters, right? So that's going to be our HCl, and that's squared. Because we're just taking the moles and liters, we're putting them together, right?
Yeah.
Just making sure I'm not moving too fast, but also not too slow. So what's my H2? 0.29 moles, still divided by the same liters, 0.125 liters to the first power. And then the other one is chlorine, so 0.45. You guys are calculating for me? Over 0.125 liters. Yeah. Oh, I didn't mean to put that. My bad, guys. I looked at 1.25 and then I somehow wrote. This is a decimal. This is a decimal. My bad. I was looking at the decimal up here. Thank you. See, Lucas is the only one that'll be honest with me. The rest of you guys are just big chillin'. I don't know where my calculator is. If I were a calculator. I was like, it's under a paper. Anybody? Any takers? 1.55. I'm going to verify that. Yes, that is correct. Mundo. 1.55. So Kc is equal to 1.55. That tells us that the forward direction is favored. All right, this is wrapping up from yesterday still. So this is our Kp now. What is my equation that relates Kp and Kc? Kp is equal to parentheses RT. Thank you. It does make a difference. And what is delta N? How do you find delta N? It's not just moles of what in the reaction of the products. It has to be gaseous, right? If we're talking about pressures, you have to be talking about gases. You can't be using solids, liquids, and aqueous. It's about the gases. So this is calculated by doing moles of gaseous products minus moles of gaseous reactants. Okay, so looking at my reaction right here, it said assume everything is gaseous. How do you know that, Alvin? Alvin said Kc equals Kp.
There's zero change in moles.
Okay, so how does it influence my math? Okay, great. So this is not a calculation question. This is a thinking question. If you see that you have one, so that's 2 moles total of gaseous reactants, and then you see here you have 2 moles of gaseous products. The difference here is 0. Anything raised to the 0 power is 1. So then that would make Kc equal Kp. So Kp equals 1.55. Yeah.
Okay, so say there was, just say like in the reactor there was 3 moles and there was 2 moles, so that goes to be 3 over 1.
It would be, you said 3 and then 2?
Yeah.
So it'd be, that's a good example, and I'll kind of write that up here with us, if I can get those board to work here. Okay. So if it were 2 moles of gaseous products minus 3 moles of gaseous reactants, that would be -1, right? So whenever I do Kp is equal to Kc RT to the -1, this R value is what? 0.0821. Okay, so 0.0821 times probably around, well, it depends. I won't say around room temperature, it could be really anything. It depends on what the temperature is, how different this value is going to be, but whenever you do something to -1, what are you doing actually to the math here, or in the math here? So you're dividing by RT, correct? So this is now Kp is equal to Kc over RT, based on that -1 being there. So if you divide by a decimal, let's say 0.1, what does that do to my value of Kp? Makes it bigger. So sometimes based on if there's less gaseous moles made, many times the Kp will get bigger. yeah, less gaseous moles made of products versus reactants, the KP will get bigger. So you can also do some calculation estimates by looking at the math of how many of those things relate. Now, let me pause for a moment. You guys do oh no, let's take questions first. From your textbook questions, our textbook homework, I'm going to take a couple questions, but I'm not going to take all of the questions right now because I can do some of them shortly. Yeah, I'm ready.
Why is it like units per tank?
Because it's a ratio. It's because it's a ratio between the relative extent of reaction of forward versus reverse. So from the textbook questions, I'm going to take a couple. You guys shout them out. Yeah.
Can you go over 50?
50. Another one. 23.
So from 31.
31. 23, 31, 50. Let me start with those. 23. This is, I might have to look at the question. The concentration of the reactants will be greater equilibrium. Oh, this is about the relative differences between the reactants and products. I might have to pull the questions, guys, because I don't have it memorized. If I leave that there right there for a second, whoever asked me 23, change check. I only have the book out at this point. 680 something. On person whoever asked 23, also the odd ones are in the back of the book, okay, in terms of answering some of these too. So can I move on from 23? The question for 23 was, when the reaction comes to equilibrium, will the concentrations of reactants or products be greater? Well, the K value tells us it's to the negative fifth, 10 to the negative fifth, so reactants should be highly favored. All right, what was the other question, 40? Oh, 31. Did I make up 23? I thought somebody asked me 23. 31. It's at the very bottom of my board. I can't scroll any. Oh, no, I can just do this. Maybe. It's, yeah, okay. Well, that doesn't help. Now it's just itty bitty. Okay. Can you guys see that any better? It's probably not that much better, but here we go. So 31 is the relationship between Kc and Kp. Plugging in your values, this question gave us products forming 2 moles of gas, reactants forming having only 1. So when you subtract your moles, you get 1, and then when you plug in your RT to the first power, the value of Kp divided by R and I guess it said 25 degrees Celsius. When you plug in, you should get your value of Kc. Sorry, you're dividing, so you solve for Kc using your politically correct formula. Is it just that you want to check your work, or you were confused on how to do this one? Right, so just remember the P and the C. And then you guys can check for that one in the back book as well. Alvin? There are never supposed to be units for it. It's a dimensionless constant. There should be no units at all. And so what we do is, the only thing, occasionally like on AP exam, or on an old one like from the 80s, they have KPs with atmospheres on them, but most of the time they say it's a unit loss factor. Okay, and then 50. Okay, 50 is on another document, so it's not on this one. Give me 1 second, guys. Oh, there's a nice blank page there. Let me get to that one in a second, okay? So I'm not wasting time finding on my answer keys here. All right, so let's pause for a minute. I'll go over the rest of homework, but I don't think it was too much of a stretch because there's a lot of K setups and then that politically correct formula and then some of the content, like the basic underlying understandings. All right, so now we're gonna do some ICE boxes, okay? So this is including not only at equilibrium conditions, but conditions that are they're called initial, which we recognize as like the beginning of a graph. So on a graph like this, you'll see this is an experiment that you actually have to be setting up a similar experiment to this. But they've set up 3 experiments. Here's the particular reaction of interest. And with this reaction, you start off in 3 different ways. 1 molar of a product, 1 molar of a reactant, 0 of the products. That's the first one, which you can see from this graph over here. You can see they start with 0 here and 1 here. And then 1 molar of each of the two products and 0 of the reactants. So you can add whatever you want to. I'm calling them reactants and products based on their location in the balanced chemical equation. And then the third experiment, they just put 1 molar of all of them. And so after some time, so you see that we start off in different locations here, 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 and then all three of them start here. What do you see happens eventually over time? Say again? They all reach equilibrium, right? They all meet a consistency in concentrations. But you'll notice is they all meet at different concentrations. This is the same reaction there, right? Two HIs makes H2 gas and I2 gas. Their value for K is exactly the same. So if I'm telling you their value of K is exactly the same with all of these different concentrations, I'm basically saying that the ratio of relative reactants to products should still be the same. So we're going to verify that now. So from the data here, which has the concentrations given to you, guys see that decently enough? I want you to calculate K for this reaction. You might want to go ahead and set up, actually use this equation. Set up your expression first. We're going to calculate this right now. I'm going to separate you guys into 3 groups real fast. So 2HI yields hydrogen gas and iodine gas, or iodine solid. And did you guys get the K? What's the K expression for that particular one? Over times. I'm going to make it gaseous right now because I said solid because generally iodine is solid, but it's likely a gas in this question actually. I2. Okay, so this is our K expression. You two tables do question 1 or experiment 1.
Oh wait, yeah. Yeah.
Oh yeah, because it formed
Yeah.
products. Yeah. Sorry, I just like to listen to you guys because you guys are my smart cookies. I like to agree with you. That's all right. I've heard it from many of you who've been wrong. Okay, so these front 2 tables do this one with these values. Jack's table do this middle one. If you can't read it, I might need to read it to you. And then that side of the room do these values. Plug them in and let's see the K value. Can you guys read those values? This says 0.213. This says 0.320. This says 2.360. Yeah.
So for the products, does that mean hydrogen and iodine are both that concentration, or like the
No, they're each that concentration. I don't know, about 50. I have it right here, but I'll flash it up. It must have lost come back to you in black.
Okay, yeah.
I was like, hold on, I want to see this.
You got 0.01.
All right, verify with people at your table or who did your experiment. All right, experiment 1, what'd you guys get? 0.0.
185.
What did Jack's area get? 0.0183. And this last table area?
0.0184.
Oh, slam dunk, people. It's basically the same, right? So it doesn't matter where you start. If it's at the same temperature, which we're assuming that these 3 experiments are the same temperature, it doesn't matter if you have 1,000,000 moles of products and 0 moles of reactants, or 1,000,000 moles of reactants and 0 moles of products. If you let them react, they will get to their equilibrium spot. They will get to where they're stable. They will get to an appropriate ratio, even if the concentrations at the end are different. Do you see how that works? So it doesn't matter where you start or where you end. Their ratios will always be setting themselves up for their relative reactants to products to be the same. At this point, though, you should be able to tell me who's more stable, the reactants or the products, for this particular reaction. The reactants are more stable. The reactants happen to be hydrogen iodide, right, or hydrogen iodide gas, or iodic acid, or hydrogen iodic acid, hydroiodic acid. Gosh, I can't talk. And that makes sense because these 2 gases by themselves are probably a little more energetic because they have less properties of stability amongst them because of nonpolar bonds. Nonpolar molecules. Okay, so that's just some proof of concept for you. Next, we're going to actually do some ice boxes. So, have some space in your paper, and I'm going to explain the logic as we go. But what you should see, and actually I'll show you that back on this graph, what you should be able to see are 3 points to these graphs. You see an initial at time 0. You can pull data from a graph for the initials. This one's a little harder to see. Let me go over here, because that's like a really tiny slope. Okay, so start over. You guys should see an initial here and here for these particular reactants and products. You should see some change. So it's going from whatever that concentration is at 1 molar to like 0.2-ish moles or molar. So there's a change occurring there. There's also a change occurring here. Change, and then we should see an equilibrium position here, meaning their final concentration. So their change is not like the point at the C, it's the difference between the initial and the middle. So as the reaction occurs, we have an initial. We start with initial. There's change that occurs, and then we have a final point, which in our BDA tables we call that after. But for our equilibrium tables, we're going to call that E for equilibrium. So we call it initial, change, and then equilibrium. And we're going to we can look at it from a graph perspective, but most of the time we look at it in a table perspective. Questions yet? Yeah.
So the slope of that line, or the blue line is twice as much as the red line?
So that's a good point. The change for one reactant or product will be different from another reactant or product based on their stoichiometric relationships. Yes, that's a true statement. This is changing twice as fast as this one down here is. And we're going to see that in a table too. Good point. Can I go forward to the ice box? Okay, so in this example here, we have a reaction given to us. This reaction is a 1-to-1-to-1 mole ratio. This is question 4 on your lower right-hand side. It says equilibrium constant notes problems. Do you see that on your packet? Lower side. Okay, I'm doing number 4 right now for you. So at some point, you're going to see that the words in the questions will either say initial or it'll say at equilibrium. So this particular one says a student places blah, 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 blah in a flask. The reaction shown below is allowed to reach equilibrium, which means that this stuff up here is talking about the initial conditions of a reaction. So as it's allowed to reach equilibrium, it was found that in the flask it contained this much of the PCl3. So we're going to set up an ice box, which is a rice box. I don't like to call it a rice box, it just feels awkward coming out of my mouth. But we have a reaction, which is here. That's our reaction. We have our initial conditions that we're going to write here. We're going to look for the changes that occur over the course of the reaction. And then E is when it meets equilibrium, what are their concentrations? It's very similar to a BDA box, but we're putting what unit in there instead? Either pressure if it's talking about gases, or concentration if it gives us information about concentration. Well, this one gives us concentration information, so I'm putting concentration molarities in there. So initially, they placed 0.2 moles of PCl3 and 0.1 moles of Cl2 gas and a 1 liter flask. You guys can divide by 1. What's the molarity initial of PCl3? 0.20 molar. What's the initial concentration of chlorine gas? 0.1 molar. What's the initial concentration of phosphorus pentachloride? Does it give us anything? No. Initially, the student did not put anything in there, so it's going to have 0 molar. Okay, so over the course of reaction, some changes are made. Well, we don't know those just yet, but we do know one other piece of information. It was found that at the end, the flask contained 0.12 moles of phosphorus trichloride. Where does that go in my chart? Equilibrium under who? Phosphorus trichloride. Okay, so we know that at the end, it says 0.12 moles, but divided by 1 liter is 0.12 molar, right? So what was the change that occurred over time? It decreased by what? 0.08, right? So this decrease right here is for every one, is in the ratio of 1 to 1 to 1 here, right? So as I subtract from one reactant, it's reacting with the other reactant, right? it's got to also subtract from this one as well. It just happens to be a 1-to-1 ratio, so it's the same. So I'm subtracting 0.08 molar here as well. Well, I can't subtract from products 1 because I have 0 products right now. But what's true? As a reaction occurs, as reactants are consumed, products are produced. So I'm adding to this side. Does this look very similar to a BDA table? Right? So 0.08 molar is formed here. So at equilibrium, once the equilibrium point has been met, I have 0.12 of this, I have 0.002 molar of this, and I have 8 of this because I'm already at, I have 0 plus that, right? So these are now the equilibrium values. What do I do with this now? Oh, I'm sorry, there's questions below this. We didn't even look at the questions, we went for it. If I were then to ask you something, it would likely be, what's the equilibrium constant? So what's the question? Is what's the K value? I heard 0.08 over.
Yeah, it's just you have an extra 0.
Oh, I did put that in. Sorry, I was listening, I believe. 0.2 molar. Yeah, 0.02 molar. Okay, but regardless, if I'm plugging into K values, I would set up my K expression, plug in my values, and I would have a K value. What's your question, Alvin? Thank you. Sorry. All right, so this is our ice box, and we did it by looking at changes because we knew the final, so we had a chance to just find the C value. Sometimes we don't know that much information, so I'm going to show you that as well. So one, we were able to set the initial concentrations because we did moles per liter. We're good with that. What were the changes? We were able to do that by looking at the initial and the final. What were the equilibrium concentrations? We subtracted and added. If you had to find Kc, you could do that, yes? All of these are 1, 1, 1. So I'm just going to show the process of, what was this over here? Phosphorus or pentachloride over phosphorus trichloride times chlorine gas concentration. So you can plug your values in there. I'm not going to do that right now, if that's okay. How would you get the Kp?
Always.
Kc or Kp?
You can say KC, KP over RT.
Okay, you're going to go ahead and, well no, we already have Kc. We're solving for Kp, right?
So KP equals
RT in parentheses to the delta N. What variables, or what would we be plugging in here? So, do we have a temperature given to us?
But you gotta change it to
That's Celsius, right? So you gotta plug that in for Kelvin. So Kp is equal to whatever this Kc value is that we get over here. Plug that in. My R constant 0.0821 atmosphere liters per mole K. Okay. Oops. What's my T value? What's 250 plus 273? 523 Kelvin. Okay. To the what power? Why -1?
Because the moles for KCO5 is 1 and the moles for KCO3 plus 2 is 2 times 2.
Good. So product moles minus reaction moles as they're in their gaseous phase. So you just raise all that to the -1 power and then calculate. Give me a double thumbs up if you're able to move. Yeah.
So if there was like a mole ratio, would you just do like a fraction like you did in the BDA chart?
Yes. And I'm going to get you an example like that. So her question was, if there's a mole ratio being other than 1 to 1 to 1, basically, if it were like a 2 right here, you would say twice as much chlorine gas is subtracted. So you'd say twice as much here. But this would still be a 1 because it's only a ratio of 1. We're going to get you an example like that in a second. Yeah.
So the delta N only relates to the coefficients?
The delta N only relates to coefficients of gases. Yes. All right. I think we're good. Am I fine to move on? Okay. Thank you. I just need your feedback. So, this is a question that was instigated by, I think, Courtney's previous teacher about the difference between Q and K. So I gave this information of so much of this reactant and 0 products. It was an obvious choice which way we were going with this reaction, right? We had to go in the forward direction because there were no products. We couldn't go in the reverse direction because there was nothing to react. So I made it very obvious that you would subtract from the reactant side and add to the product side. But what if I give you concentrations for every single reactant product? So in that last example, if I had said A plus B equilibrates to C, if I'd given you 1 molar 1 molar and 1 molar, how would you know which way to proceed? Well, let's say I give you the K value, because I would have to, because you don't have any information to plug into K, right? So you wouldn't know. So your choice here is like, do I proceed forward, subtract reactants, add products, or do I proceed in the reverse direction, subtract products, add reactants? But you don't get to choose. You have to prove it to me. So this is what I think Corey's group was talking about yesterday. Q is equal to K and so forth. If Q, which is instead of exactly the same as your K constant, Q, which is, for this one, just plug it in as A, B, C, and D. This would be C raised to the first power over AB raised to the first power as well. I would just be plugging values in here, and let's say this was 2. When I plugged these initial values, in here, let's just say that's 2. And I told you in this problem up here that K was equal to 0.1. Well, I have a problem here, right? Because I have a Q value of 2. I have a K value of 0.01. I'm definitely not at equilibrium, right? Because my values are not at the appropriate concentration. But relatively, who do I have more of? Reactants or products if my Q value is high, right? So logically this should make sense, because if my Q value is too high, I'm comparing 0.1 to 2 right here. I have too many. Just get it out, Vinky. Just like in the movies, just rip open the candy bag. It's only to disrupt you for like 2 seconds. Okay, so 2 products. Trying to be a stealthy ninja. If anybody else has a snack they'd like to eat, that's fine. Okay. Lost my train of thought. Huh? No, the cookies are gone. I maybe ate like 10. I feel really bad about it too. Okay. I have some bananas. If I could possibly finish this problem, that'd be great. Would anybody like a banana?
Yeah.
If you can catch me. I hope you guys can share. Oh, I was gonna let you have it. Jack can share with you. One of those is gonna be mine, but you guys will. Sorry, that's good. I'll go start. All right, so back here. Are you ready? All right, so my logic here is you can understand math, right? You shouldn't have to memorize mathematical relationships. You should understand them. So if I'm comparing an initial concentration of Q and my equilibrium constant of K, and I said Q is greater than K. My problem here is that I have too large of a Q value, which you guys said meant too many products. How do I get rid of products? Do I go in the forward direction or the reverse direction? You go in the reverse, because you react your products to form reactants. So this K right here being Q greater than K means I have too many products, so I have to get rid of products, which means I have to proceed in the reverse direction, which means proceed left, because you're going to the left, correct? Okay, so as you consume products, you're forming reactants. That's going to help balance your Q out so that it equals K. Your goal is to get your initial concentrations down to be the equivalent of the equilibrium concentration, so you have to adjust by adding or subtracting reactants or products. So mathematically, if Q is less than K, my Q being concentration of products initial over concentration of reactants initial, what's my problem here? Do I have too many products or too many reactants? Because it's going to pull the value down, right? Because a large denominator means the value gets smaller. So if you have too many reactants, you need to proceed which direction? Right, you're going to proceed right or towards products to increase the products so the numerator gets bigger, and decrease the reactants because they get consumed to make the denominator smaller, so it balances out. So eventually Q can equal K. Q represents the initial concentration before the reaction even ever began. Question?
That's what I was gonna say.
What is Q? So yeah, so K is basically from that last example. Q would be, if I had the opportunity, I would plug these values in as my initials, but this was an obvious one which way it proceeded because I had 0 products, whereas K is plugging in your equilibrium concentrations. Yes,
you'll always be given K, and then you'll have to like solve for Q, so you can just like compare.
Yes, because you can't find K if you don't have equilibrium, right? All right, so let's do a question related to this. I didn't say this, but when they are equal, it's at equilibrium. I think that's now apparent though. You guys have some, you guys have some examples, which are, organizing my places here. Do I have this on your paper? I may not have this on your paper.
No, it should do. It's the number one.
Oh yeah, sorry, I skipped to number 4 earlier. Now we're back on number 1. So for an example like this, walk me through it. How would I determine which way it proceeds? Go ahead, Jacob. I'm ready.
You find Q, you have to set down Q's concentration, right? So you have to, Q equals the concentration, I know it's just squared.
I'm just going to plug in my expression first. Okay.
Over.
Okay, so for our Q expression, that's our expression. We'd now be plugging in our initial concentration. So the initial concentrations being all of them 0.1, yeah?
Okay, so since they're all the same, couldn't you just cancel out those
Yeah, so I'm going to pull this down here because I need some space. I need some space. Okay, so to simplify this, when you plug in your 0.10 molar squared, 0.10 molar, and 0.01 molar squared, you should simplify that immediately. So then your Q value is 0.1. Well, Q is not molar, if Q is 0.1, got such bad habits of putting my units on everything. Okay, so this is Q. Compare that to K. Who is greater? Who's greater? Hold on. Q or K is greater? K is greater than Q. So the problem is you have too many reactants because Q is too small. Is that what you're saying? I'll write it the way I had on the previous slide. It's a little bit easier to see. Q is less than K, right? Q is less than K. Q is too small. How do I get Q higher? Proceed to form more products. Okay, I just want to make sure you know all those things mean the same thing, right? Because when Q is less than K, that means there's too few products, or AKA too many reactants. Yeah. No, it's equally favorable in both directions. It's already at equilibrium. You're done. Mm-hmm. So, if you have too few products, you must proceed, right, to form more products and remove reactants. And so the word proceed is the word we use for this. We're going to use the word shift later with Le Chatelier's principle. Okay, can I move on from here? Let's do one more like this. Maybe tell me how this part B is different than what we just did.
You don't have like concentration up right now.
So what do you have to do?
Find it.
Do you? No. Okay, so first off, I do see we need to find molarity, right? So we're given moles and we're given 14.5 liter. So we can find the concentration of NO2 here. That's by doing moles by liter. And we can find the concentration of oxygen here by doing moles per liter. Are these reactants or products? One's a reactant, one's a product. So we're not given information about who. So nitrogen monoxide, we're assuming, if we're not given concentration information for that, we're assuming the concentration of nitrogen monoxide is 0. Okay, so if this is 0, sorry, I have to keep going back up. If this is 0, which way do I have to proceed? Without a doubt. Why do I have to go towards the products? You can't go in the reverse direction because then you'd be subtracting something from nothing, and that can't happen, right? If you have a 0, you have to proceed to form it because you can't subtract from 0. Mathematical sense.
Yes.
Yes.
If we were given like the molarity, and we already have a K value, why shouldn't we just go with this?
These are not molarities at equilibrium. These are assumed at this point in time. I'm telling you right now, considering this direction, or considering this reaction, which direction does it proceed if I give you these concentrations initially? So these are initial concentrations. Good point. But yeah, I would have to tell you initial probably a bit more in depth. All right, and then for the last one, what would you have to do if I give you nitrogen monoxide, nitrogen dioxide, and oxygen gas? What would you have to do to figure out which way this proceeds? Plug it into the Q. Okay, so these are all initial, not quite concentrations, but we can divide by 10 liters to get concentration, right? So we'd first find all the molarities, and then we'd plug it into Q, and then you compare Q and K, determine which way it proceeds. Give me a double thumbs up if the concept makes sense. You'll be practicing this a little bit more. So this is just initial concentrations. You must plug into Q, and this is with initial concentrations. And then from there, you figure out which way the reaction proceeds. On top of that, though, we can do a problem like, once it proceeds this way, what's the ending concentrations, which is what we're going to do next. So we're applying this next. Okay, just making sure I'm not leaving you in the dust here. So this is the question set, that's number 2 on your packet. And I just want to make sure we're able to see an ice box. I'm going to do numerous steps here. But this is an ice box. My reaction is up here above. If you want to make this a little bit bigger, this might help. Let me put mine directly on top of my boxes. So this is what Courtney was asking. What happens when you have a different coefficient? How does that affect your ice? So your initial concentrations for A and B are 0.2 and 0.25. Your initial concentration for C here, assuming, is what? 0, because you're not given any concentration information. So over time, this is 0 time, this is delta, meaning change. Here, I'll actually say ice here. This is my initial, this is my change in time, this is that equilibrium. We assume it's at equilibrium, but I'll show you how we know that in just a second. So, what's my change over time here? Minus what? 0.05 molar. How do I know? Well, okay, never mind. You know you're subtracting from the side because 1, the value is smaller, and 2, you can't subtract from the products because it's already at 0. So as I subtract 0.05 here, what do I have to subtract here? Why 0.1? 2 versus 1, right? I'm actually going to write that as a 2 times 0.05 molar to represent that coefficient as a stoichiometric comparison. And then over here, I'm going to add how much? So just 1 times that, so just 0.05 by itself. So at this end point so far, I've got 0.15, I've got what here? Keep this in your head. 0.150 molar, because this is minus 0.1, and this is 0.05. All right, so at this point, I have a new setup, so restart. I'm starting off with blank, blank, and blank. I could say, all right, guys, let's take these these initial concentrations, plug them into Q, compare Q and K, and figure out which way it proceeds. But you'll notice I don't give you a K value, right? So we're going to keep proceeding the same way we are just right now, because this is more for an example purpose. So now I have initial, change, and equilibrium. Notice I give you a point of information down here. I have already added something here. What did I add? So add 0.025 molar. Yes. Subtract what over here? So this is going to be the 1-to-1, right? So A is a subtract 0.025 molar, and B is subtract 0.5. I'm just going to write it as, for my purposes, minus 2 times the X value that's being subtracted. So then this one's already set. What's this at the new new endpoint? 0.125 molar. So that's 50 minus 25, right? 25. This is okay. So at this point, what you could do is you could graph these individual points. So at 20 seconds or so, you have each of these values, you graph them. At 40 seconds, each of these values, you graph them. And then one more. We're going to do another one. Starting off again, so this is my I for ice, initial, change, and equilibrium. At 60 seconds, I have 0.07. Hold on. Start me off. How did I get from here to here? Okay, so I minus 0.03, which was 2 of something. Okay, that was 2 of. Okay, so that's minus Rx, which is the portion that's subtracted from each of these in their appropriate ratio. So I'm subtracting this same amount over here, but not times 2, so 0.015 molar, and I'm adding what over here? Just plussing, or adding the 0.15 molar that we quantified based on the ratio 2 here. So the ratio is important, right? And we went ahead and we already knew what the amount that was relatively subtracted or added to each of these, because we had a final amount. But what we're going to start to see is that if I don't know what the change is, I don't just say, flip the table, I'm done. I can't just be done with the question if I don't know what the change is. I can plug in a substitute there, and I can call it x. We're going to learn how x can help us solve for our finals now. So these are called ICE boxes. Are you guys feeling okay about ICE boxes right now? Now, at this point, I'm not at equilibrium, because you'll notice that, let me kind of show you this for a second. You'll notice that at equilibrium, my values should be consistent. Like you did yesterday with the straws, 3 times had to be consistent. Well, I'm just going to go for B right now. At 20 seconds, it was 0.15. At 40 seconds, it was 0.1. At 60 seconds, it's 0.07. Are we at equilibrium yet? No, because we're still changing concentration. We're not at a constant concentration yet. So you could see a graph coming from this and actually graphing it to see when you met equilibrium based on the time that it was a consistent value. Very similar to your graphs should be similar to from yesterday. Okay. I'm not going to do this question. You don't need that one. We already did that one. Okay, let's do I want to do this one?
Yes. No.
I didn't highlight it. I want to highlight the ones I want to do. How would you do this one? It doesn't say at equilibrium, but it also doesn't say at initial. I'm assuming this is at equilibrium right now because we don't have any other information. We don't even have a K value. So what would you have to do here? But you don't have a K value to compare, so you can't figure out which way it proceeds. You're assuming, good point, if it doesn't tell you which way it proceeds and it doesn't give you a K, you're assuming it's occurring in the forward direction because you don't have any other assumptions that you can pull from. So I would have to write my equilibrium expression first with the products over the reactants. That one reactant is cubed, correct? Right here. And then plug in your values and calculate K. I'm not doing this question. Can I move on? Okay. The one I want to do is here. I was like, I knew I was going to get to the one. Because after some point in time, I think you guys get it. And that's not, I don't want to do that one now. Let's do this one. Okay, I'm to the point where I want to do one. So during the experiment, each of those values are given. The reaction was allowed to reach equilibrium. What concentrations of each of those would occur at the end? Notice that we're given our K value. Tell me how you start this one. So set up the Q or set up the equilibrium expression. So I'm just going to say K is equal to, what's my expression? So HI squared, we're doing products over reactants. So we just did a very similar example, or at least expression. All right, so that's our K expression when we have our K value is 49.5. All right, tell me how I go from here. Okay, I can find molarity. I can divide by 1 in my head. I can do that. What's next? Into Q. Okay, so this essentially is equal to Q, right? The same setup as Q. When I plug in, what's the hydrogen iodide? What do you see? Okay, so it doesn't say. So do I need to solve for Q? Jacqueline? Not yet. So let's pause for a moment and let's recollect. So you guys were like, okay, find Q. So I was going to find Q, but do we have enough information to find Q? No. What do you notice we don't have any of? The product. So which way does it have to proceed? towards the products. Got it? So this is how you'll normally start. This is how I start problem 2. You start going because you just know the flow, and you're like, wait, I don't have to do that. I already know that I'm at the middle step now. So I'm going to take my information and plug it right into my ICE box. So what do I know initially? What do I know initially? Molarity of who? So 0.200 molar, because that's 0.2 divided by 1 liter. And the same for the iodine. You should be writing this example down. We have 0 products initially, so I'm trying to align them underneath my reactants of products. There's just a small space here. Okay, so over time, this reaction happens. You know you have to proceed which way? To the right. Okay. I don't know how much is being subtracted. This is where I get to plug in x as my placeholder, because I can solve for x using algebra. So how many x's are subtracted from these two? 1 x is subtracted because it's got a 1 coefficient. The same thing here. 1 x is subtracted because there's a 1 coefficient. But how many, comparatively with the stoichiometric relationship, how many x's are added to the products? 2. Not because you're adding these two together. Because what? Because of the 2 ratio here. Okay. So at the end, I know what's here. I just don't know the exact value. I know it's going to be 0.200 minus x. This is 0.200 minus x. And this is an equivalent of 2x out here at the equilibrium point here. So knowing this is equilibrium, and knowing this is my equilibrium constant, and this is my equilibrium expression, I can solve for my products, my equilibrium concentrations. I just got to do some math. You ready? She says with a smile. Okay, so this is your HI, this is your HI, right? So 2x squared, thank you, divided by, these values go into the H2 and the I2. How can I simplify that a little bit? Right, so I can either say 0.2 minus x times 0.2 minus x, or I can just say 0.2 minus x squared, because it's the same thing, right? That equals 49.5. How do I simplify this to then solve for x? Square root both sides. If you can square root it, you're in a good place. Square root on both sides, that simplifies this to be what? 2x over what's 49.5 square root? 7.035, thank you. Okay, keep simplifying. Let's solve for x. What I need to do? Multiply by. So this is going to distribute up over here, right? Okay, so then 2x is equal to 7.035 times 0.200 minus x. And then I would distribute in, correct? All right, so once I distribute in, then I need to do what with my x's? Add it over, right? Because it'll be a subtraction. Meaning collect your x's, right? Combine like terms. I'm trying to impress you with my math vocabulary. So this is 2x. I don't know what this times this is.
14.07.
What's this?
Oh, 0.14.
0.1407?
1.407.
Yes.
1.
I thought it was 1 and not 0. Okay, 0.1407. I should just calculate this, but I like for you guys to be yelling numbers at me all at the same time. Okay, so then that's what you get, and then you add your 7x on this side. And I'm showing literally every step for you right now. I make too many assumptions about math, so forgive me if you're like, geez Louise, she's showing us baby math, but I just got to make sure we're good. So this is 9.035 x equals to 1.407, so I'm going to write that down, right? And then do what? Divide by 9.035, 9.035, and x equals 0.156. Something like that. Okay, that's what x is. Is that our answer?
No.
That's my x that I can go, all right. Now we plug it in, right. So what's 0.200 minus 0.156? And that's true for both of these, right? 0.044 molar, right? That molarity equals Is it 0, 0, 0? Is it 2 zeros or 1 0?
1 0.
1 0. Yeah, okay. That's the concentration of H2 and I2. Yes? And then this is 2 times 0.156 molar, which is 0.3,
1.
which equals the concentration of HI. Whew! I'm tired. That was a long one because it gave us no information for our finals. You had to do a substitution of X. Set your substitution of X as equivalent to your expression and then your K value itself. Do some math and solve for X. Now, I don't need you to support me through the entire math process. Like, I understand you guys can do, you can probably get here. Like, I want to see the substitutions into the expression, at least to here. And then if you're going to go from here down, I'm cool with that. You'll track your math, you'll be successful. The problem is people, you do a lot in your head and sometimes you're not as successful. But if you trust yourself and you can get from here to your final, I'm okay with you not showing me all of this, but give me some support so I know that you're plugging in correctly. The other thing is, do you guys know how to use your solver and your calculator? Some of us do and some of us don't. Okay, so let's just do a quick practice with that. Who has a 80, what is this?
84.
I don't know how to do it on yours, so I can know how to do it on mine. So go ahead. Vinky, tell us, narrate for us, and tell us what you would be plugging in here.
Okay.
All right, listen, I'm not teaching Vinky. Go ahead.
Alright, so you go to y equals and plug in 2x.
Hold on, can you pause for a second? Let me just ask for advice. Isn't there under math, there's a solve under 0?
I was going to graph it and then find the intercept.
Okay, you could graph and find the intercept. Let me see if I can teach you something then. Is there under math a solve function? Okay, so go under math, function, go to solve, which is I think 0. And then it says 0 equals something. So 0 equals something. Well, we right now don't have 0 equals anything, but I can easily say 2x divided by parentheses 0.200 minus x, and I can subtract, right, 7.035 on both sides, and I've essentially set 2x divided by this minus 7.035, I've set that equal to 0. So I've met the qualifications that it requires you to put into the solver. But in your solver, you have to make a guess. So once you hit enter, you have to go back to solver. So once you go back up. So when you hit enter on the equation, it's going to say x equals 0. You have to put in a guess. Put in like -1. And hit alpha, enter, because that's an alpha solve. You see it? You guys see it?
I know what I'm doing. I'm pressing out.
Whatever you choose.
Alright, I'm just making sure you have a secondary backup. Give me a thumbs up if you got 0.1557. 1557. Alright, people with a calculator like this. Did you get one? I'm taking a quick break because I'm going to do like 3 more examples. You can do like Take a quick break if you're taking a break. But then you would still subtract, right? Oh, so you're just saying. Okay, so then you have to do fine.
But it's also like good to like zoom in and out sometimes.
Does it take a little more time? Okay, so it's all going to be a secondary tertiary backup for you. Alright, I'm giving you 1 more minute to practice with solver. If we have to practice that later, that's okay.
Yeah.
What's up?
What guess that?
You have to guess a number. You have to put in something for to prepare and then it's calculated.
So whose is that?
It doesn't matter what number you use.
Sometimes it'll say error, so if you put in 1 and it says error, try -1, because it's basically trying to do quadratic equation, the plus and minus thing. Okay? Alright, and pause for me on that solver features. Go ahead and finish your conversation if you're finishing something. I do want to move on, so that's something we can continue to practice. Okay, and back to me in 5, 4, 3, 2, 1. Showtime. Next question. Set up how you think you should set up. I'm trying to give you an opportunity to get the hang of this before you leave me. Set up this question on paper, not in your head. Some people who don't like to write anything. As far as you can. What have you guys done so far? Set up an ice box and then what? I hear you say plug in what? Initial concentrations and then what? Okay, you're subtracting X from which side? Okay, so far you guys are saying 0.033 molar and 0.00810 molar and 0 because you were given 0 there. Alvin, what's up? You can get crafty, but you will never see it like that on any of the like AP exam style things either, because they always just do it with respect to the coefficient at hand. Good try. You could. It'd work out though. So then you're going to subtract. So basically, it's from the respective 0 products. You can't subtract from products. You must proceed right. So as you proceed right, you know that you're subtracting from the reactants 1x and 1x because that's their coefficient, and you're adding to the products with respect to its coefficient. So you get 0.033 minus x, 0.00810 minus x, and 2x. Has anybody even set up the K expression? Okay, first thing you do, okay, thank you. I will always try to recommend that you do that at the very beginning, because by the time you get into math, most people forget to do the coefficients as exponents when they start their K's from there. So it's just to save you from making a mistake. So the K expression is nitrogen monoxide squared over nitrogen gas and oxygen gas to the first power each. And our K value, guys, look at the value of this thing. What does this tell you? Okay, yes, it is a small number, but what does it tell you? Like, not only favored, but like so favored, so favored. Do you even think, like how big of a number do you think X is to be forming in products? Say again? Almost 0. It's going to be so negligible, it's so tiny, it's basically 0. However, this reaction occurs just a teeny bit in the forward direction because it's an equation reaction. We're going to have a couple, just a tiny amount of products, but basically the relative concentrations between the initial concentration of reactants and final concentration of reactants, it's basically not going to change that much because the value is so small. So this is a point to note. I'm going to teach you how to neglect X. If the value of K is tiny, like 10 to the negative 31st, 10 to the negative 10th, 10 to the negative 8th, 10 to the negative 5th or 3rd maybe. It just depends on the relative concentrations. If it's really tiny, you can likely do something called neglect X. And we'll talk about that right now, okay? Because basically what would we have to do right now to solve for this X? So you plug in, right? Plug into our K expression. So K expression says nitrogen monoxide, which is 2x squared, right? Plugging values in, over 0.033 minus x, which is the first reactant, and then the second reactant, which is not the same, so it basically means we can't do that square root everything like we did on the last problem. If it were the same value, we could square root the whole thing, and we'd be in a good place. But we got different values for the reactants, and then we have it equal to 4.8 times 10 to the negative 31st. Mathematically, what would you have to do to solve for x here? A lot is not a mathematical relationship. It's a quadratic equation, people. Negative b plus or minus the square root, plus or minus the square root.
B squared minus 4ac all over 2.
That thing, right? You guys didn't learn to row your boat?
Yeah.
Okay. Well, you're missing out if you didn't learn it that way. But I have to go, okay, multiply, FOIL it out, multiply by this constant, combine like terms, so I'd have to get like, you know, ax squared plus bx plus c is equal to 0. And I would have to plug it into the quadratic formula, solve for x, and then double check that the x's match with, when I plug them in, they match my k value. Ain't nobody got time for that in AP chemistry. Okay, so this is the problem. If you get into a place where you have to do a quadratic equation, double check and say, is my k value really tiny? If it is, it's likely that the x that, the x that's being subtracted here is so negligible, it's basically 0. So negligible, basically 0, still will have a value, and that's what we'll solve for. So what you do is, for neglecting x, what you do is you assume that the x here is approaching 0. So I draw an arrow through it and put 0. That's representing that x is so small. It's so close to 0, we say it's approaching 0. This is approaching 0 as well. But you're only doing it for x's that are added or subtracted x's. This x, we can't call 0, because then I would have a 0 on the top of my numerator here, which would totally not equal my k value, right? I can't plug a 0 in for this x. So do you know which ones you're showing as approaching 0? Yes or no? Only the ones that are being added, subtracted, not the one that's a singleton by itself. So how does this simplify my math? You have a question?
Yeah, so like, what's the value that like defines that x is like negligible?
So we don't have the x value, we have a tiny k value, right? Tiny doesn't have a number.
Okay.
And I'll show you how we check this with the p-value of negligible 5% in statistics. Do you know what I'm talking about? 5% rule in statistics. It has to be on the lower margin of error so that we can make this assumption. We'll do a 5% rule check at the end though. Okay, so a small of a k value, especially if you run into a quadratic equation. So how does this simplify our math? This is gone. I'm not going to put x there, it's gone. This is gone. Now, how do I solve for x? Multiply up and then what? Divide by 4 and then square root, right? Much easier. Definitely not easy, but much easier. So then go ahead, multiply 0.33 times this guy. I'm doing it with you so I know that I can hear what numbers you're saying. So this is, I'm going to rewrite this as a simplified version. This is my note to myself that you can use your solver. I already showed you that. So this is 4x squared over 0.000267, which is equal to this guy. Multiply, divide by 4 square root. X equals to anybody got it yet? Times 10 to the... Look at that value, guys. Is that pretty close to 0? I'd say so. So our assumption, this is molarity, right? So when you solve for x, did I go too quickly through that? Are you guys okay? Are you guys okay?
Yeah.
Okay. When you solve for x and it doubly verifies that your assumption was correct, you're in a good place, but you're still not finished. So this value is very close to 0. Our assumption that it's approaching 0 is highly probably correct. But the way you verify that you were able to neglect is you have to show me that you met the 5% rule. I'm going to come right back to this question. Here's my little explanation for you. So read this and write down what you need to. We're going to go back and verify this. So when you do simplifications with x's, we call it neglecting x. And you can only do this when the value of x is very small, meaning that the forward direction doesn't occur much and there's very little products formed, very little reactants subtracted, showing that the reactant concentrations initial are very similar to the reactant concentrations at equilibrium, meaning essentially they don't change that much. So to verify that, to give you a point of like when do I neglect x, if you're starting to get into square roots, the quadratic formula and like cube roots and stuff, you're likely working too hard, and you'll maybe do that in college, but you're not going to do it right now with me. It's likely a neglecting x problem. It's a sign that you're probably going to need to simplify your math. So the rule of thumb is that this will only work when you have less than a 5% difference or less of what your x value could have been to what it is right now whenever you have calculated it. So neglecting x is going to be only when your statistical probability of having a small margin of error works out. Who's taking stats? Who can explain this in chemistry terms? P-value less than 0.05 or greater? Do you know what I'm talking about? Significance of what?
It's like a significance of like if you're lower than that, then if you're lower than the 0.05, then you're favoring
What I've assumed,
Yeah.
like we have.
Yeah,
So
yeah.
it's basically saying that when I make that assumption, my error isn't so great that my value is wrong. It's saying that my error is so small that I'm essentially right when I make that assumption. Okay, so it makes our math easy. So deal with this. Okay, so with respect to the x we just found, what we have to do to show our 5% rule is that we have to take x divided by the smallest quantity we would have subtracted it from. Who's the smallest quantity we would have subtracted it from? Say again? 0.00810, right? This guy right here. So we take the x and we compare it to the smallest value we added or subtracted it from, and we multiply by 100, and we see is it 5% yay or nay, or is it less than 5% yay or nay. So that value is, let's go ahead and plug that in. So 5.664 times 10 to the negative 18th divided by 0.00810. I know that's way less than 5% because look at the differences between these exponents. 10 to the negative 18th versus this. Times that by 100. What's your percent? Times 10 to the negative 14th percent. It's like 0.00000% error. That ain't nothing in that. That's like a drop in the bucket compared to 5%. So it's definitely doable. That basically means when you've shown me your percent is less than 5%, that means our assumption is valid and that we can neglect x and we don't have to go back and do the quadratic formula. So when would we neglect x? When do we trigger that thought of maybe I should neglect x? K value is very small, meaning we proceed in the forward direction very minimally. What's another trigger that would make you think about neglecting x? No, the concentration being different can still be is still doable if you don't run into the what when you're solving. Right? The likely quadratic equation, you can maybe neglect x. That will not be all the time, but most of the time it will, especially if you get into cube roots and stuff. Okay, we'll do some more neglecting x tomorrow. I think you're done for today. Your brain's probably saturated. If it's not saturated, you have 8 minutes right now, and you probably should start. Is a problem set called? It's a problem set. It's got 9 questions on it. Turn to the second page. It's called AP Chemistry, Calculating Equilibrium Concentrations. Questions 1 through 9, and answer these at the bottom. Go ahead and look at this for a moment, and then I'll collect my thoughts on what I want to do. I said we do, I'm sorry. Is she actually going to do something? Usually Jack wants to know. Are you guys good? Do you know what I'm talking about here?
Yes.
Appreciate you. Start with this. I'm just making sure it's at the end of the pages today.
Me and my Courtney have a group message called Smart Asses.
That's verbal out. That's okay. I can't remember if y'all's class or another class. Let me pause my video. Hold on.
Oh.
No.